Okay, we're going to do a little demonstration here. I just adjusted the volume on my computer microphone, so we'll see if it works a little better. I'm going to do an example of a logic signal and how to decode it into a binary number. So in logic signals, you typically have 0 volts to represent a 0 and some other voltage to represent a 1. It could be 5 volts or 3.3 volts or 1.8 volts. It depends on the system and the technology that you're using. So for transistor-to-transistor logic, or TTL technology, which is what we'll be using mostly in this class, we have 0 volts to represent a 0 and 5 volts to represent a 1. So quite often you have to string those or stream the zeros and ones or 0 volts and 5 volt pulses across a wire to transfer data from one device to another device or across the network, for example. So if we were to stream a series of zeros and ones across the wire, you might have a signal that would look like this on an oscilloscope. So I could have a 0, a 1, a 0, let's say 2 ones, 0, and we'll say 2 more ones. So we have 0, 1, 0, 1, 1, 0, 1, 1. So let's say this is our signal here. So this is a 0, a 1, a 0. This is 2 ones in a row, a 0, and then this is 2 more ones in a row. So as you can see here, we have 8 bits in binary. Now, if we assume the right-hand bit was the least significant bit in this case, it could be streamed either forward or reverse. Most significant bit first, the least significant bit. But for this one, we'll assume the right-hand bit is the least significant bit. So I'm going to write this number out as a binary number, 1, 0, 1, 1, 0, 1, 1. Right? Now, we can convert this number to decimal by taking each digit multiplied by its place value, and in the binary number system the base is 2, and the exponent on the base starts at 0 on the right and counts up as you go to the left. So the least significant digit is times the base 2 to the 0 power. And then it counts up on the exponent, so times 2 to the 1 power, times 2 to the 2 power, times 2 to the 3rd power, times 2 to the 4th power, times 2 to the 5th power, times 2 to the 6th power, and then times 2 to the 7th power. So we're going to multiply each digit by the base raised to the exponent. And if you have 0 times anything, it's going to be 0, so we don't need to include the zeros. So we'll start with a 2 to the 6, so 1 times 2 to the 6. And then we're going to have 2 to the 4th, so we're going to add 1 times 2 to the 4th. And then we have 2 to the 3rd, so plus 1 times 2 to the 3rd. And then we have 2 to the 1 power, so plus 1 times 2 to the 1 power. And then finally 2 to the 0 power, so plus 1 times 2 to the 0 power. So 2 to the 6th power is 64. Plus 2 to the 4th power is 16, so plus 16, plus 2 to the 3rd power is 8, plus 2 to the 1 power is 2, plus 2 to the 0 power, anything to the 0 power is 1, so that's plus 1. So we add all these numbers up, and we get equal to 91, right? 91. So that's our answer. 91 is the value that was sent across the serial line. Okay, so that concludes this short little video demonstration on how logic signals are transferred across a wire serially. That's one wire, one bit at a time, as opposed to parallel where you might have 8 wires or 16 wires or 64 wires, and each of them carrying a bit at the same time. So I could 8 bits sent in one cycle or one clock cycle. Where here on this serial communication, it could be a synchronized communication where I have a transmitter and a receiver. So the transmitter sends a signal from here, and the receiver receives the signal over here on the right-hand side. And they're both synchronized so that the samples are read at, let's say, this point here in the middle, here, here. So the signals are read like at the points where the X's are, so it can receive the correct data at the right time. Okay, so that concludes this video. We'll do another demonstration on parallel data. Thank you.